I am a researcher. In my field of expertise is computer science. Most specifically, it's artificial intelligence. And since last month, I started on this new project that is called Deep Wetlands, in which we want to quantify the water extent changes of wetlands by using deep learning. I'm sorry to disappoint you a little bit. In this case, I'm not doing a deep dive into a topic, but more like a general overview of the work that I will be doing in this project. As I told you, we started last month. So let's get started. Yeah. So here's what we're gonna discuss during this talk. We're gonna talk about wetlands, and we're gonna talk about the challenges that we have in this project. We're gonna discuss a little bit about remote sensing, deep learning. Then we go a bit deeper and more specific to convolutional neural networks. And then we show how we can apply all of this tool set to map wetlands, and then finally we close with the expected outputs. So we have wetlands, and the definition of wetlands by the Ramsar Convention is that they're areas of marsh, fen, peatland, or water, whether natural or artificial, permanent or temporary, with water that is static or flowing, fresh, brackish, or salt, including areas of marine water, the depth of which at low tide does not exceed 6 meters. So as you can see from this definition, there's no very specific frame to know what a wetland is or is it not. So this itself poses a challenge in identifying the wetlands. We'll see that there's very different types of wetlands. There's swamps, there's bogs, there's marshes, there's fens, there's mangroves. And our goal is to know where they are in Sweden. But why are we studying wetlands? Why are they so important? Well, wetlands are crucial for humans because of many reasons. First, wetlands prevent floodings. So when there's very a lot of rain or high tide or things like that, they kind of stop the water from going into other places like cities. And they also sequestrate CO2 and and it prevents it from going into the ozone layer. So, it helped us mitigate the already big problems we have with climate change. They're also home to a wide variety of plants and animals. They purify the water we consume. And finally, they also serve the purpose of recreation. So, many of us over the weekends or in the summer, we go to some type of wetland just to have some leisure activities. The problem is then that in the last 120 years, 70% of the worldwide wetlands have disappeared. And if this tendency were to continue, we would have very, very, very big environmental problems. Therefore, we need to know where these wetlands are and how they are changing over time so that we can identify which ones are at a risk of disappearing and do something about it. So this is the grand challenge of our project: quantify the changes in wetland surface areas on existing wetlands. To accomplish this, we have 3 specific challenges that are to create to create a diverse annotated data set of Swedish wetlands. We also want to create a machine learning model that is able to take multiple remote sensing inputs in order to create an inventory of existing wetlands. And finally, we want to have a tool to visualize the wetlands inventory and their changes in water extent over time. So the first, let's talk about mapping wetlands and why is it a difficult problem. There are a few reasons why this is a difficult problem. The first one is that it's very costly to have people, go on to field trips. Let's say everyone around Sweden, and delineate or detect the limits of the wetlands. This is not only costly in the sense of resources, of time and money to go into these sites, but in many cases it's also dangerous. If we have areas that are very remote, or if we have areas that are very hard to access, something like maybe near a glacier or something, can be quite dangerous. So this is a reason why we don't have a very accurate map of wetlands nowadays. The other thing is that we have that wetlands are constantly changing over time. So depending on the season or depending on the year, the extension of the water can change. So the limits of a wetland are constantly moving. So for instance, here we have a map of a wetland, and we can see that in 9 months, the change is very drastic, In this first, in August 2013, we have a lot of wet fields, but in April 2014, we have a lot of dry land. So, to be constantly going and surveying what wetlands are, it's not something feasible. Another challenge that we have is that if we're using remote sensing data, if we're using optical satellite images, and then we start having problems like, clouds and shadows can make it difficult to identify where the wetlands are. So as we can see in the image on the right, cloud prevents us from seeing the surface, but also the shadow makes it difficult to know what's beneath. So this is a challenge. And then the last challenge we have is that sometimes when we have a lot of vegetation, a lot of dense vegetation, it's very difficult to know if there's water underneath or not. So, if I show you this, you wouldn't know what type of forest it is. And for instance, this image is from a mangrove forest in the Caribbean coast of Colombia. But as you see, it's very difficult to know if there's water underneath this or not. So we have to overcome this as well. Then we have remote sensing. Remote sensing is the process of monitoring the Earth's surface or the atmosphere by using readings from either satellites, airplanes, or drones. So what we will integrate into our project are essentially 3 types of remote sensing data, and the first one is optical. So the optical, it's called, it's a form of passive remote sensing where, the satellite or the device is not emitting signals, but it's just receiving signals. So we have the sun goes into different types of surfaces, and the sensor of the satellite receives the bounces from the surfaces. The second type of remote sensing data that we're going to use in this project is called synthetic aperture radar, or SAR. The idea behind SAR is that the satellite is emitting or sending microwave signals to the Earth's surface, and with the bounce that the satellite receives back, is going to identify what's on the Earth's surface. So here, the length of the signal, the longer the signal is, the more it can penetrate, let's say, vegetation. So for instance, if we're using an L-band signal, we can actually penetrate the vegetation and get to know what's below the vegetation. So we can actually reach water, and this is going to tell us a lot, like it's going to help us identify wetlands. So just to give you an example, I have taken a photograph of a wetland near Stockholm. This is a wetland just in the north of Västerås. This is the optical image, right? But as I will show you now, there is a lot of water hidden under the vegetation in this wetland. We cannot see it with the optical image, but we will be able to see it with the SAR image. So just so that, I'm not showing you different places, it's the exact same place. I want you to look at this reference point. I want you to look at this road and at this lake. And I want you to see how this is not changing, this is not changing, but this is changing, okay? So as you can see, there's a lot of water. For instance, this leg of the water is not seen in the previous image. So there's a lot of water hidden under the vegetation. That's why we need these SAR signals, or these microwave signals. The third type of data that we're going to use is called InSAR, and it stands for interferometric SAR. So the main idea behind InSAR is to take two SAR images and compare them at a different time. So if the surface has changed the elevation, for instance, if there's more water, the water level is higher, then with the InSAR images, we're going to be able to detect that change. This is because when we have the phase of the signal, we can see the changes between the signal phase in the two different time steps. So for instance, again, this is an image from the Caribbean coast of Colombia. And here we have a mangrove forest. And, in this image, we can say, okay, there's some water and there's some forest, but we cannot know if there's some water. But by using the InSAR images, we can see that there have been a lot of movements or there have been a lot of changes in the surface level. So by using that, we can actually detect water. Okay, that's enough about wetlands and remote sensing. Now we're going to talk about deep learning. So the main idea here is that, okay, what's deep learning? Deep learning, basically, it's a subfield of artificial intelligence in which we use a very specific type of algorithm called artificial neural networks. And the main idea behind deep learning, and why it's performing so well, or why it's so popular nowadays, is that with traditional machine learning algorithms, after some amount of data, the machine learning algorithms are not able to improve. So regardless, if I give it more data to okay, sorry about that. So basically, the main advantage of deep learning algorithms is that with more data, they can actually make better predictions. And the larger the amount of data and the larger the size of our neural network, the better the predictions are going to be. Yes, so let's talk about then about convolutional neural networks, or CNNs. So basically, the main idea behind convolutional neural networks is that they're really good for processing images. They help us to analyze images and detect what's on the image. And one of the main questions you ask yourself when you're about to process an image is, how can we translate a photograph into something the computer can interpret? So here we have an example of a very simple image. This is the letter A. And we can see how this image is represented by using numbers. So we have a number from 0 to 1 that encodes the amount of brightness of a pixel. So if we see here in this part, like the white pixels are all represented by 1.0, and the black pixels are all represented by 0.0, and the gray pixels lay anywhere in between. So the main idea is that we can then use image analysis to do several types of tasks. The first one is classification. So we give it a picture and we identify what's on the picture. So here we know, okay, there's a person, a dog, and a sheep. And then we can also do detection. So, it's a bit more elaborate than classification. So it tells us where the cat, the dog, or the sheep are. And finally, we can do segmentation, where we actually delineate the shape of the body of what we're interested in. So for our project, we're interested in doing image segmentation to identify and delineate where the wetlands are. Why convolutional neural networks? Because they represent, they consider not only pixel by pixel individually, as many machine learning algorithms do, but they also consider the surrounding of each pixel, which contains valuable information for make classifications. And they also preserve the geometry of the image. So, we always know like the proportions of everything in the image. And they automatically detect features without any human supervision. So, in our machine learning algorithms, before we give the image or to the algorithm, we have to extract or manually create some features. I'll give you a very simple example. Back in the day, before we were using deep learning, we, like scientists, for instance, if they were going to detect or they were trying to know if there was a cat in an image or not, they would have like these kind of techniques in which they would identify the shape of the ears. If he has pointy ears and a small nose and a bit of hair coming out of the nose, it's probably a cat. In this case, you would need expert knowledge to do that. But deep learning is a data-driven approach where the features are calculated automatically by the algorithms, and you don't need to manually build features. And they have also superior performance to compared to traditional machine learning approaches. So the main, here is like one of the most important competitions that is held every year in the field of computer vision is called Imagenet. In Imagenet, we have a very big data set of images, very small images, and it contains several types of let's say animals. We have dogs, cats, horses, birds. We have also vehicles like airplanes, trains, trucks, ships. And the main idea is that we want to detect what's on the image. So in 2010, when this competition started, like the error rate was of 28%. But next year it was down to 26%. So 1 out of 4 times you would make an error. But it was in 2012 with the algorithm AlexNet that the first convolutional neural network was able to outperform other types of algorithms. These gray bars are traditional machine learning algorithms, and the blue bars are convolutional neural networks. So after 2012, every single winner of the competition has used convolutional neural networks. And more importantly, in 2015, the algorithms were able to outperform humans. So that says a lot about the power of these algorithms. I'll just show you very quickly, and it's a very it's just an overview of how it works. But we have an image. This is how a convolutional neural network works. We have an image, and then for each, we take, let's say, little segments of this image. Let's say a 3x3 segment, so 9 pixels, a square of 3x3. We apply a filter to it, and then after that filter, we output one more pixel, let's say, or one more value. And then we start doing that, little by little over the whole image until we generate what we call an activation map. You can think of an activation map as if it was a filtered image, the same way you do filters on Instagram, right? This is not the same, because we can have like negative values, but just for the sake of understanding. After we have an activation map, we can actually do something called pooling, in which we reduce the size of the image. Then we can actually put another filter on the reduced image, and then maybe we can reduce it again with pooling. And at the end, we give it to a fully connected neural network, which it will classify this last activation map, and will tell us if, for instance, when we give it this image, if it belongs to a car, a truck, a van, or a bicycle. So we're just going to see a little bit how it works in a bit more detail. This is what I'm telling you about, how we use filters to build activation maps. So we can see that we go on, a square of 3x3 at a time, and we generate one more and one more and one more and one more until we have built like the entire activation map. And the activation map, it's just here, you can either call it kernel or filter, but basically we just multiply each pixel value by a weight that we learned during the training phase of the algorithm. So, as you can see, we're just multiplying A by W, B by X, and E by Y, and F by Z. So it's not really rocket science, okay? And then we have the pooling. So in the pooling, what we do is, there's several ways of doing pooling, but the most common one is called max pooling, where we take the maximum number out of a set of numbers. So for instance, for this four numbers. If we take, what's the maximum of these four numbers? 6. Very good. So we have a 6 there. And what's the maximum of these four numbers?
Might be
8. Perfect. Then we have 3 and 4. Now we have reduced the size of our image. It's as simple as that. Okay. But then, how can we apply this to map wetlands? So, this is the big question. So in our project, this is what we're going to do. We're gonna work with these 3 work packages, that I described before as our specific challenges. We're going to collect and annotate a diverse data set of wetlands. As I was telling you before, these algorithms need data to be trained. So we need to collect and delineate these wetlands so that we give it the algorithms a ground truth. Then we're going to be a network that takes 3 different inputs. It's optical images, SAR, and InSAR images. And once we have this, we're going to produce a map in which we have identified the wetlands. After we have that map that we have identified with wetlands, we're going to have several maps over different periods of time in order to visualize the wetland extension changes over time. And the main idea is to identify which wetlands are at risk. So to prevent them from disappearing. Okay. So far, I haven't told you anything like too crazy. So, why is it until 2022 that we're waiting to do this? Why is it possible now, and why wasn't it possible 30 years ago? Well, there's 3 main reasons. Nowadays, we have more data that is freely available and then that it's openly available. Let's say 30 years ago, we didn't have access, or we didn't even have the Sentinel or Landsat satellites in orbit. And we didn't have access to the data of satellites, open access. So since these algorithms are hungry for data, and I'll talk about that later, this is something that it's really convenient. Then we have more powerful computers. With the rising popularity of video games, the industry has developed more and more powerful graphics cards that have hundreds or thousands of processors that can help us do calculations, like many calculations in parallel. So that has enabled us to train algorithms in a much faster time. Before we could train algorithm for months or years, now we can do it in hours or days. So that's one of the reasons. And the third reason is that we have better algorithms nowadays. I showed you how convolutional neural networks changed the landscape of computer vision in 2012. But then we still have a few challenges remaining. I told you these algorithms required a lot of data. They're data hungry models. So this is a problem that we have because we actually need a lot of delineated data, a lot of delineated maps that we have to build manually in order to give it to the algorithms. That's very time costly. And then we have the algorithms that we have to design. They're going to have multiple inputs of different types of data. I showed you before a convolutional neural network, but it's just taking an image, an optical image. But now we're going to have a hybrid of optical, SAR, and InSAR. There lies a challenge in itself. So to solve the data hungry problem, we can use something that is called transfer learning. In transfer learning, okay, no, before talking about transfer learning, I'm going to show you a typical deep learning algorithm. You train your deep learning algorithm with a lot of data. You learn the algorithm learns some features, and then it can make some predictions. But what happens if we don't have this many data? The algorithm is not going to perform well. Well, there is a way in which we could train our algorithm with a smaller data set, and it's to take a pre-trained algorithm, a pre-trained convolutional neural network that has been trained on a very different data set. So we could train our data set on, puppies and kittens, and we can actually then fine-tune it to recognize cars. It's because, like images share some common properties. So in this way, by having a smaller data set and a pre-trained deep learning algorithm, we can actually have a very similar or equal to performance than compared to an algorithm that it was trained with a large amount of data. Another way in which we can solve the data-hungry model problem is by using data augmentation. So, for instance, we have an image here, and this is from a paper where they were trying to recognize buildings. So we have our image here, and what we can do is we can apply transformations on the image, so we have more data from the same image. So, here we just do a vertical flip, a horizontal flip, we rotate it, we transpose it, we scale it, or we crop it. And in all of those cases, the algorithm should be able to recognize where the buildings are. So in this way, if we take a map of a wetland and we mirror it, or we crop it or something like that, in all of those, it should be able to recognize where the wetlands are. So in that way, out of a single image, we can have like 10 or 20 more. So yes, that's another technique. So what we want to do in our project is to unify different types of images into a single deep learning model. Here I have something that is called a Siamese convolutional neural network, and it's called Siamese because it shares parameters between the two networks. So the main idea here is that we're going to train with two types of images in parallel in order to have like a unified model that can help us identify wetlands with using optical, SAR, and probably InSAR as well. And these models, like here I have one where we have the three types of images, and we do a bit of data augmentation, and then we can give all the data to the convolutional neural network model. So the main idea here is as I'm telling you, to solve this computer science challenge in having multiple heterogeneous inputs and be able to unify and extract like all the best information out of it. So that's our like what we're where we want to go. So just to wrap up here, what do we expect out of this project? We want to first, produce an annotated open access data set of Swedish wetlands. We want to produce a map of the Swedish wetlands. We want to produce a novel convolutional neural network algorithm that works with optical, SAR, and InSAR images. And we want to produce a timeline visualization of the wetland extension changes over time. And of course, the last thing we want to get out of this project is publications. After all, this is science. So that's it. Thank you very much. I would be more than happy to answer your questions. Thank you.